All right, guys, welcome to day two of our week two. Today we're going to be talking about statistics and some basic concepts in statistics. So, let's get you to find the resources for today's class. The same thing we had like the day one. You go to Dr. Heha Academy on GitHub, and then you go to the repository for week two. So when you click on this, you're going to find all the materials that we have for the whole week. So we can locate for week two, day two. This is our RMD file, which is the coding file. And also this is our notes. And also we have a knitted note for the RMD file of both the code and the output. So let's get to class. So this is our note for today. And for today's class, we're going to be talking about statistics. First of all, we have to understand why we even need statistics basics in AI. So let's go through our modules for today. Okay. Okay, hold on. I don't know why that is glitching. Give me a second. Okay, I think we're good. All right. So for the overview, we want to know why does statistics really matters in AI, and of course, we have to talk about the probability basics. We have to talk about random variables. We have to talk about expectation and variance, common distributions. We have to look at specific examples, and also the big part, the law of large number, and then of course, we're going to have an exercise and we have a cheat sheet. If I were you, I'll keep that cheat sheet. Anyway, so because we have quite a number of topics that we want to cover, we might not be able to cover this in a class. So we might probably take about 2 or 3 days to cover this whole thing. This is just to help you grasp the foundation of statistics, and subsequently we are going to be referring to some of these things. All right. So before we talk about the concept, let's talk about statistics itself. Why do we learn statistics? Because, first of all, for any AI models you see out there, the big models that you see in top companies, it is as good as the data that we feed them. So the quality of the data is what contributes to the performance of the AI models. And because the AI models go through rigorous training, which comes from of course, the good quality of the data, and then the training process is what helps the performance of the AI model. And when we're talking about the quality of good data, it comes from statistics, because statistics has provided us with the tools that help us to understand data itself, that help us to clean data and to summarize it in a way that is good enough to be passed down to the AI model. So statistics is like a very big part in any AI model, because we have to go through statistics to get a good model. And of course, the probability and random variable, they are the foundation of machine learning. And then, of course, we can say that without statistics, AI becomes a black box, because we can't interpret how do we validate and how do we trust the results that is coming from the AI models. And we have added some written examples here in AI. Take, for instance, like the self-driving cars, the chat GPT, the medical AI. We have so many examples that we can all see around us. All right, so let's move on to the next one. Let's talk about the probability basics. But before we do that, I'm going to take us to our notes and then do something that I want us to remember when it comes to statistics. So that is going to be your cheat sheet. So you know how the whole concept of statistics comes about and why it is very important. Okay, so let's pick okay, let's drawer, and then I'm gonna pick this, and then let me okay. So let's talk about statistics. Right. So when we talk about statistics, it starts from, let's say you have a population. We have a population, and because in research, it is very hard for you to use the entire population to do your research or to make a conclusion or to do whatever. It is the best thing to do, but naturally it sounds like it's not possible, because take for instance, you want to do like a medical, maybe you want to understand the differences between maybe the high blood pressure taken by a machine and the one taken by human. If you need to use the entire population of people to do that, it sounds impossible. So that's why from population we need what we call a sample. And how do we get a sample? How are we going to be sure that our sample is a true representation of our population? So we use what we call a probabilistic model. So we use that. Let me change my pen to, let's say, red. We use what we call a probabilistic model to select a sample from the population. And at the end of the day, what do we intend to do with the sample? After getting our sample, what are we doing? We do what they call a statistic inference. So you can see we do what we call a statistic inference. And after making our inference on the sample, what do we intend to do? We intend to make a valid conclusion and generalize whatever is going on with our sample on the population. That's why it's very important that our choice of sample is a true representation from our population. I hope that clarifies this. So this is like the whole thing about statistics, the whole concept behind statistics. And you see this probabilistic model, you see this statistic inference, they are a whole different, because by the time we start breaking them down, each one of them has so many other things embroidered inside. Okay, so let's go back to the notes and move on to the probability basics. So when we talk about probability is talking about the measurement of a certainty, right? Take for instance, you want to perform an experiment, let's say flipping a coin or rolling a die. You do not know what is going to come up when you try to do that. So we call that probability of uncertainty. We don't the degree of uncertainty, the degree of you don't know what is going to come up in the experiment. So that's just the basic idea behind probability. But we have some axioms of probability. When you look at this omega, we call this omega. That's the probability of omega. Let's go back to our notes. Let's add a new page here so that we call this the probability, right? So we can call this probability. So we said probability is what we said is the degree of a certainty. You can find so many definitions out there, but this is just to simplify it. And I just said that we have what we call the axioms, like the properties. So we have what we call probability of omega, right? Or probability of the entire sample space to be 1. The meaning of this, we call it either omega or s. We'll call them sample space. And what do we call sample space? Sample space is the total possible outcome. Is the total possible outcome. Total possible outcome in an experiment. In an experiment. Take for example, we want to perform an experiment that involves rolling a die. So let me move this down so that we can have this as an example. Experiment example now. Let's say we have an example right here and we want to perform maybe rolling a die. So when I say rolling a die, it means we are doing the experiment once. So the total possible outcome we can have in a die. Remember, a die is six-sided, right? So we can have 1, we can have 2, we can have 3, we can have 4, we can have 5, and then we can have 6. So these are the total possible outcome in that experiment. So we call this in statistics a sample space. We call this a sample space. And the axiom we have earlier that was talking about the probability of this omega, which is the probability of this sample space, is 1. It means that when we sum the probability of each one of this outcome in this experiment, it must be equals to 1. That is a major axiom in probability. Another important axiom is that the probability of all the each one of them must be between 0 and 1. So you can say 0 less or equals to, let's say, maybe a particular event, let's say probability of A must be less or equals to 1. So this is saying that the probability can only be between 0 and 1. You cannot have a probability that is greater than 1, and you cannot have a probability that is negative or less than 0. So it can only be between. And when you have your probability to be 0, when you have the probability of, let's say, A to be 0, it means that the event cannot occur. The event cannot or does not occur, because you're very sure that it's not going to happen anyways, right? So in that case, we can say its probability of that event is zero. But when you have probability of A to be one, that means you're saying that this event is going to happen. You are very certain, 100%. Right. So the event is going to occur. So that's what we mean by the axioms that we have all discussed here. So when we say probability of A should be greater than zero, but it must be greater than or equals to zero. When it's equals to zero, it didn't happen. We also have some relationship with some, we can even connect it to set operations. Let's say probability of A union B is going to be the sum of the two probability minus the intercept of the what they have in common. So we can look at a typical example like when you toss a fair coin. Let's say you toss a coin is two-sided. Either you have a head or you have a tail. If I ask you for the sample space in that part, it's going to be heads equals to head, comma, tail. And for each one of them, they're going to have unbiased. So it's going to be there's a particular English we use. So they're going to have a fair probability. Each one of them are going to have point 0.5 as their probability because they both have an equal chance of occurring in the experiment. Does that make sense? So yeah, so that's what we mean in that case. So we also have a setup for this in R, right? It doesn't just as we compute it manually, we can also write a programming code to compute this. And that's what the next chunk is saying. So when you set your seed, I'm sure in your first week, this has already been covered. Why do we even set seed? The major reason why we do that is for reproducibility. Because when you are generating something and you're not setting your seed, every time you run that code, it's going to keep generating different set of numbers. Okay. But when you set your seed, every time you reproduce, you generate that same data and then you can generate the same result. So we already use the function called sample. So the function sample, it takes the argument x, which is the possible outcomes you can have in that experiment and what is the total number, how many times are you performing the experiment, and then we have some other arguments in the function, and from there we can compute the mean. We can do so many other things. Let's move on to our coding and show you how this setup works. So the first thing I always say is clean your global environment, please, so that you don't have overriding situation. So let's run this code chunk. When you run this code chunk, you can see ignore this error warning message. This I should have set my seat, but there's no need for that anyway. So what this is doing is when you do that 10 times, these are the possible occurrences that we can have because of how we have set our seat. And if you count that, we're going to have 10. So we're saying what is the mean that the tosses is going to yield head. So it's going to look for how many cases are we having head, and it's going to compute the average of that. It depends on whatever we're trying to achieve. This is just a basic example. Now let's go back to our notes and get back into the next thing. So the next thing we're going to be talking about is random variables. What do we mean by random variables? Random variable is telling us about how do we map an outcome to a real number. Take for instance, let's go back to our notes and add something very important. So we're gonna add another page and call it our random variable. So for this case, we're gonna call it random variable. Okay, so we're gonna call this our random variable, right? So in our random variable, we can say RV. We have two cases of random variable. You can have the discrete random variable and we can have the continuous random variable. So you can say continuous from the definition. A discrete means a finite number or let's say an integer number. Let's call it integer number. A specific value. But when you say continuous, you're talking about range or interval or something like that. So that's what we mean by discrete random variable and continuous random variable. And we also have these two cases in distribution wise. We have some specific distributions that's discrete distributions, and we have some that they are coming from continuous. Anyways, let's go back to our notes so that we don't go outside what we are trying to cover. All right. So take for instance, they gave us a specific discrete example like a Bernoulli. So like I said earlier, we have so many type of let me change my pen. So we have so many type of distribution. Let's say the smallest or the smallest of discrete distribution is Bernoulli, right? So when we say Bernoulli, The next one will be binomial. And we have so many more distributions under each one of them, which we'll be talking about later in the class. Here we can talk about uniform. We have a lot. We have normal. We have exponential. Just a lot of them. Anyways, let's leave it like this so that we don't divert too much. All right. So when we look at this specific example, they say we have a Bernoulli distribution with the probability of success to be zero point 0.5. So for us to express that in a Bernoulli distribution, we have two possible outcomes, whether you have a success or you have a failure, right? Remember how we denote our success. When we say success, it means when you get one. When you get zero, it means when we have failure. So because it only has zero and one when you put in your x. So each one of them is going to take the same probability. And that's why in this setup, we have the two of them to be zero point 0.5. Take for instance, we look at a continuous case like a standard normal distribution. You know, standard normal distribution is a special case of normal distribution with mean of zero and variance of one. Okay, so when we look at the case of a standard normal distribution, we can see how we can set this up in R. You guys should notice something very important in the R code for Bernoulli. Bernoulli, there's no function called R Bernoulli in R. So it uses R binomial. But what it's going to do is it's going to set the size to be 1 for it to converge back to Bernoulli. That's very, very important in Bernoulli setup because there's no function specifically for Bernoulli, but we can use the binomial R binom to get to Bernoulli by setting the size equals to 1. And also for the standard normal distribution, we just need to use the function R norm and then take the size, the mean, and the standard deviation because you have to be careful of the arguments. Let's go back to R code and demonstrate what I just talked about. So when we come here to our R code, okay, so when we come here to our R code, we can run this code chunk. And then we can see for Bernoulli distribution, what do you notice? We only have 0, 1, because that's what the size is going to take. It can only take either a 0 or a 1. And then we have 10 of it. And for an R norm, we have the 10, which is the sample size. When you count this, you are only going to have 10. The mean should be 0 and the standard deviation should be 1. So another cheat sheet I will give you is whenever you get confused about the argument, how do you know what you are putting first? Go to your help function here and type in the name of that function. Take for instance, this is R binom. So I'm going to type R binom, and when I do that, it's going to pop up and I can see the binomial distribution. So from here, I can read the argument and the description on how that function works. So when you go through all of that, you can see this is for a density binomial. This is a probability binomial. This is a quanta binomial. And this is the one we use to generate. So we have the cumulative distribution function. We have the probability density function and we have the quantiles, like I said. So you have to know what each of those functions, what arguments they are taking, so that you can use that to construct your code. That's something I find very helpful. And when I get stuck, when I'm writing my code, I go to my help function. I try to see the argument of that function to help me construct it. Because if you don't do that properly, it's either you get a wrong result or you get an error code. All right, guys. So let's go back to the class. So the next thing would be moving on to expectation and variance. What do we mean by expectation and variance? Expectation means the average just as we compute the mean. But when we have distribution cases, how do we get our expectation? Now we talk about different cases here. We talk about the Bernoulli, we talk about this. So let's move to the next page and call that our expectation. So we can use this and call it expectation. We can even say random variable, right? So when you say expectation, we can have the mean. Let's say mean in this case. If you have a discrete, let's say discrete. So let's do this. Discrete and a continuous. Because remember, we have different distribution that fall into different categories. It depends on where this distribution is coming from. So if you have a discrete distribution, the expected value of x is going to be summation of x. You can say p of x. Then you take the range of x. But if you have a continuous, it's going to be integral of x f of x dx. Then you have the range of x. This is very important. The range depends on the type of distribution you are working with. This, we call it the probability mass function because it's a discrete. The f of x, we call it probability density function. So these are different. The same way we have expected value of x. Remember, expected value of x in this case is like our mean, is the mean in both cases. So you can use this expected value to apply it to both cases when you have a discrete distribution and when you have a continuous distribution. So the next thing we're going to do now is what? Move to the variance. So when we're talking about the variance, we can use expectation to express the variance of any of our distribution, whether it's discrete or continuous. And the formula to do that, let me write this here, is expected value of x squared minus expected value of x all square. Okay? So remember, this is like our mean that we computed. So it's like saying that expected value of x squared minus what? Mean square, which you computed earlier, right? So now you need to express this. So let's express expected value of x squared in both cases, right? So let's express this in both cases that we discussed, both the discrete phase and the what? And the continuous phase. So remember, we already talked about how to express it for the mean. So for the expected value of x squared now, let's do it again. Okay, let me get a ruler. Where is my ruler? Okay, so I'm just like this. All right, so we can say expected value of x squared can be expressed in both the discrete and what again? And continuous, right? So for discrete case, we can say it's going to be summation of x squared, what? P of x, range of x. And this is going to be integral of x squared, f of x, dx, right? Range of x. This is how we do it. So when you are able to solve this differently and you solve this differently based on the type of distribution you are working on, then we can go back to that and get the variance. Because one of the major, we have some keynotes when it comes to any distribution. We want to know the mean of that distribution, and we also want to know the variance of that distribution. Of course, we have some advanced things that we may want to know about the distribution, but for this level, let's talk about the mean and just the variance, okay? So another thing we can do is we can give an example of a distribution. Let's say, let's look at this. So this is what I just discussed about. So each distribution has its mean and its variance. That's something I would want you guys to do as an exercise. Take, for instance, a Bernoulli distribution. Let me add the page again and talk about the mean and variance. Okay. Let me see. Gonna drop this and pick a different color. So let's talk about the mean and variance of distributions of, let's say, some distributions, right? So we can look at let's say discrete now, and then let's talk about Bernoulli. So we can say let's add the mean here and maybe the variance here, right? So for Bernoulli distribution has mean p and the variance p into 1 minus p. And we already said binomial is the nth of Bernoulli. So we can say binomial is going to be np into np 1 minus p. In fact, some people call it npq, where your q is equals to 1 minus p, right? And some people call this also pq. That's right, you can call this pq or this. So it depends on how you want to put it, right? So we also have the same thing for, we have so many distributions on that discrete, like I said. So let's say for continuous case, let's use a different pen to write that. So let's say for continuous case, we can look at you can look at uniform. We can look at uniform, or you can even look at the normal distribution. Right. You can look at normal distribution. What is the mean of a normal distribution? It is mu. What is the variance of a normal distribution? It is sigma square, right? So we can look at several distributions, whether it's continuous or discrete. We can find their mean and we can find their variance. And that's why expectation is very, very important in statistics, because we can use it to express, and because we don't want to go into proving right now because that will be too detailed and we don't have the time to cover all of that. But for advanced classes, that's something we are going to do on the long run. But just to introduce you to expectation, how do we express it for the mean? How do we express it for the variance? What are the distributions that we have that are discrete? Which ones do we have that they are continuous? And how do we get their means and their variance? Okay, so I think this is going to be it for the to end this class, and we are going to continue in our next class. Have a great day. Bye bye.